Good morning. My name is Chris McClendon. I'm a consulting geologist in Mandeville, Louisiana. I'd like to discuss this morning with you my thoughts on what I think was a fault slip event happened in the late 20th century in coastal Louisiana. Over the last decade, we've learned quite a bit about the relationship between subsurface geology and coastal morphology, and this has been due in large part to university research projects that have used 3D seismic data, and those have now been integrated with the work of Louisiana Geological Survey based on LiDAR digital elevation models. In particular, two research projects have been presented at GSA, Akindamide and Dowers in 2016 and Bullock and Al in 2018. And I'll be looking specifically at the southern end of the coast, what I call the Terrebonne linked tectonic system, which has taken advantage of this research plus integration of my 40 years of oil and gas exploration in the area. And I recognize a set of fault planes that are components of the linked tectonic system. They're all named here. These faults dip, or the faults along the northern boundary dip toward the south. Those on the southern boundary dip toward the north, and they form these conjugate pairs of faults, creating an overall graben system in the center. Those are interconnected with a set of salt domes, which moved interactively with the faults throughout geologic history. So putting those in context, on the coast, here are the set of fault plains with the salt contours associated with them, and then I'm annotating the surface traces for the down to the south faults in blue, the down to the north faults in red, and so they'll be represented by those lines only going forward. And throughout geologic history, there's been an interaction between this fault system, this linked tectonic system, and deltaic deposition in the Miocene in particular. This is from the work of former GSA President Doris Curtis in 1970, outlining the mid-Miocene regressive phase deltas and into the late Miocene, and they were interactive with this fault system, the faults providing accommodation capacity, the deposition from the deltas inducing fault slip in a kind of feedback loop. And you can see with integrating the thickness map from Wu and Galloway that there was a depositional thickness within the trough and on the downthrown sides of these faults, when this is the cross-sectional expression of that linked tectonic system with the graben right in the center. Fraser did the analysis of the Holocene deltas, and the last 5 of those most recent deltas appear to have a relationship with this linked tectonic system, similar to what we saw in the Miocene. So over time, the river shifted back and forth, but the delta lobes basically moved from one set of conjugate pairs to another, the faults providing the accommodation capacity and the deltas depositing their sediments in the graben systems there. And similarly with the Miocene, you can see the interval thickness from Mark Culp's dissertation at the University of Kentucky, and this anomalously thick deposition in the modern BIRDFOOT delta, which we'll come back to, and I believe there's some significance there. And then the coastal land loss. So there is, I believe, a significant relationship between the surface expressions of these faults and where wetlands loss has occurred, and we'll revisit that again in a little more detail. I think that wetlands loss in coastal Louisiana is best understood as an event. This is from the USGS 2017 study, and the graphs are by hydrologic basin. The 2 significant land loss events occurred in the Barataria and Terrebonne estuaries, and you can see that those are manifest as hotspots of wetlands loss in those 2 hydrologic basins. And the loss peaked in the mid-1970s, has been decreasing ever since, and has actually been effectively zero for about the last decade or so. This can be related, I believe, to anomalies in relative sea level rise measured at tide gauges in the area. This study from Hyatt et al. Shows what they call water level anomalies, but these are events of relative sea level rise due to subsidence, and there's a relationship between the subsidence measured at the tide gauge and the land loss event manifest at the surface. The maximum subsidence rates measured in the mid-1970s come from those tide gauges in the area. The Grand Isle tide gauge is right here, and they can be compared with benchmark leveling surveys done by Schinkel and Duck in 2004, which gathered a body of data suggesting a relatively consistent set of subsidence values for that time period, mid-1970s to the mid-1980s. The current rates, measured by Burns et al., primarily coming from GPS stations in the area, cores, and other stations in the area, are significantly lower. And I think by comparing the two, you can see the manifestation of that subsidence event in the late 20th century. And I believe it was associated with a fault slip event. So the expression of the fault surface traces across the coast is fairly obvious relative to where open bodies of water have established from marsh. And we're going to look specifically at a couple of examples. One, the Bastion Bay Fault in Plaquemine Parish. This is the fault plane from 0 to 20,000 feet below the surface. The zero contour is the surface trace of the fault. And so you could compare a subsurface geological interpretation with the fault plane at depth, fault trace at depth, to the surface trace, and this is a geologic relationship between the subsurface and the surface. A cartoonish model of the development of the Bastion Bay Fault with everything else removed shows this initiation in a lower slope environment in the lower Miocene. Primary growth period during the middle Miocene, when those deltas were depositing right into the trough, and then the surface expression today and the structural trap where the natural gases accumulated, what is Bastion Bay Field there on the downthrown side of the fault. This is the surface trace, and this is the location of Pete Hebert's camp. Hebert spoke directly to Sherwood Gagliano when he was doing his research in this area, and Woody later said that this was a Rosetta Stone for him in understanding the relationship between faulting, subsidence, and wetlands loss. Hebert reported to Gagliano that his camp had not just lost marshland around it due to erosion, that it had actually sunk, and he could tell that the camp had lost elevation relative to sea level as the marshes around him submerged. So the camp is located right here on Bayou Ferran, part of the distributary channel network that crosses the Bastion Bay Fault, and we'll use this three-dimensional model to show thickening across the fault and thickening of these coastal deposits off the flanks of the natural levees. And so it's most important where the distributary channel systems cross the fault, which is where primary deposition is taking place, and accumulation on the downthrown side of the fault. Moving through time, beginning in 1932, using imagery from a ProPublica publication in 2015, we can see the progression of fault slip, early stages of wetlands loss in the mid-1970s, and then the big step between 1973 and 1975. So revisiting that 73 to 75, I believe that was the peak of the fault slip event, and that would occur right here on the relative sea level rise curve, and the bulk of the wetlands loss occurred during that time period, as you can see here, eventually turning the area into open water. And that is shown on the USGS land area change map, Couvillon et al., as a large area of orange and red where wetlands loss occurred. Looking at the Lake Boudreaux Fault to the west, this was one presented by Akintamide and Dowers at GSA in 2016. The fault plane similarly comes up to a surface trace, dipping down to the southwest. There is a deep expression forming a rollover anticline supporting the Lapérouse natural gas field, and then a hot spot of wetlands loss right on the hanging wall of the fault. These are the faults shown by Akintamide and Dowers in 2016, and this was a boring profile taken by USGS study by Morton et al. In 2005. And what they found was an originally continuous layer of peat, now submerged and overlain by a layer of mineral sediment of mud with a carbon date of 150 years ago at the base of it. So this is deposition that happened in the 19th century, mineral sediment on top of organic peat, and then the elevation change and submergence of that marsh due to subsidence. I believe the superposition of the mineral layer over the organic layer is significant in the subsidence in this area. So again, a progression this time done by the Louisiana Sea Grant Program, 1932, 1975, and 2014, most of that occurring in the mid-1970s. But you can see the surface expression of those faults having some significance there. So looking back at that modern Birdfoot or Belize Delta, that anomalously thick deposition begs an explanation. There isn't a logical reason, a natural reason that one delta would be that much thicker than the others. And I believe the answer is actually an anthropogenic effect, as Tweel and Turner suggested, that there was a significant increase in the suspended sediment load of the Mississippi River beginning in the 19th century due to agriculture in the basin, and that caused the significant deposition in the Birdfoot Delta. Rates of deposition much higher than I think we've seen anywhere on the coast before, and creating that thick lobe of deltaic sediments. So if we think about the areas where this deposition may have occurred across the coast, prior to the early 20th century, there were no levees. Bayou Lafourche was open here, and so sediment, this was a flood map from the 1874 flood rather, sediment was being distributed all throughout the distributary channel network during that time period. And so deposition would have logically taken place, as we saw at Bastion Bay, where the distributary channels branched out across the surface traces of the faults. This is where primary deposition would have taken place, creating disproportionate loading on one side of the fault than the other. And this is where we see the hot spots of wetlands loss across those faults. So again, we have the land loss event, the subsidence event, and looking for a trigger mechanism or a causal mechanism for that, I want to introduce the discharge of the Mississippi River over time, which we could relate to the stage or the elevation of the river. And of course, that relates to precipitation in the U.S. during that time period. I think it was this relationship between the high river stages that caused the subsidence event, and that would have been manifest by water leaving the channel through the surface aquifers, as Kolker et al. Showed was happening. That would have created increased pore pressure in these surface aquifers and would have served as a trigger mechanism for the faults. So this is the land loss event that we saw in South Louisiana, I believe caused by a fault slip event triggered by a period of high river stages. Thank you very much.